Hi everybody, welcome to chapter 7. Again, the final section we're going to be covering in this chapter. So yay! Jazz hands. I don't know. Air jazz hands. Okay, anyway. 7.4 has to do with what we call partial fractions. What are the objectives of this section? We're going to, first of all, what are partial fractions? What is a partial fraction decomposition, and then how do we find it? Okay, so let's get started. Okay, so basically we're going to take a rational expression just like this one right here. Let's say you have x plus 7 over x squared minus x minus 6. So the idea is that you can take any rational expression and write it as a sum of two fractions with first degree denominators. Okay, so basically check it out. So I can rewrite this fraction as the rational expression as is 2 over x minus 3 plus negative 1 over x plus 2, and they're equal to each other, right? So on the right side, we call these like two pieces, we call them partial fractions. And when they're together, we say, oh, this is the partial fraction decomposition of the left side. Sounds pretty complicated, but it's really not. It's basically like, okay, I have a rational expression. Now I'm going to write it as two mini fractions with denominators of linear denominators, right? That have no exponents other than 1. Okay, so that's what we said. And then here, let's just suppose we have an expression, and the book calls it nx of d of n of x over d of x, basically because it's like numerator and denominator, right? So when you have the numerator, when the numerator is a higher degree than the denominator, we use we divide, we use long division, right, to find the polynomial, and then you have like a result, right? You have a resulting. We've studied long division, we've used synthetic division to do this also, which is fine, okay? When you have this situation where the numerator is greater than the denominator, we use synthetic division or we use long division to find a new polynomial, and then plus the remainder, right, which the book calls n sub 1x over dx. So whatever, it's a remainder. And then we go ahead and we do the partial fraction decomposition of n1x over d of x. So of the remainder of the of what you originally had, right? Okay. So anyway, so that's the first thing. Is the numerator greater than the denominator? If yes, you have to divide it. Okay, and then with the remainder, then you go ahead and you do, the next steps. Okay, so the next step is you factor the denominator. So you take your rational expression, you factor the denominator, we know what that is, right? And we factor it completely into linear and quadratic factors, okay, where you have, a quadratic factor, a quadratic expression that is prime, you cannot factor it anymore, irreducible, right? And then you have a linear factor that is obviously not factorable anymore, okay? So we either have, so when we factor, we either have linear factors, quadratic factors, or a combination of both, okay? And so when you have linear factors, the partial fraction is going to include the sum of these fractions. So for every factor, you're going to have, like, of the denominator, so when we're factoring the denominator, we either have a linear factor that repeats, okay, or doesn't repeat. And if it doesn't repeat, you just have here like a sub a1 means that's just going to be some expression. I'm going to show you how to find it. And then px plus q, and you would stop, right? But then here, if you had, let's say it was repeated, it had multiplicity 2, you would have another term, another fraction, okay? And so on. And then if there's quadratic factors, it's the same kind of thing, where you have, a squared plus bx plus c to the first power, that's the first one. And then if you had a second one, you would have another one, so 2 squared, and then so on. If you had a factor that was parentheses quadratic squared, you would have this term, okay? So let's get into it. So we're going to talk about the techniques for finding partial fractions. And they're all pretty similar, but just it depends on what the denominator you have. What kind of factors do you have for the denominator? Do you have linear factors, quadratic, distinct, meaning that that doesn't repeat, or repeated, where you have like multiplicity 2, 3, or what have you? Okay, so let's do example 1, which has distinct linear factors, right? Which only occur once and they're different. Okay, so you have x plus 7 over x squared minus x minus 6. So first thing, is the numerator greater than denominator? No. Okay, fine, great. So we can start we can start this factoring. So then this is proper, so we can start factoring the denominator, and the denominator factors in 2 x minus 3 x plus 2. Okay, so we're going to have one partial fraction with a numerator constant for each linear factor of the denominator. What does that mean in English? Okay, so since I have two factors, I'm going to have two partial fractions, okay? So this is how you begin. You say, okay, x plus 7 over x squared minus x minus 6 equals, and then you just write a placeholder a over one of the factors, x minus 3, and then plus, and the placeholder b over x plus 2. So basically you're rewriting the rational expression in terms of the factors of its denominator. That's really what we're doing. Okay, so how do we get, now the next thing is, how do we solve for a and b? Okay, so what we would do is we multiply both sides of this equation by x minus 3, x plus 2, which would then leave you with x plus 7 on the left-hand side, and then you have a times x plus 2 plus b times x minus 3. And that's true for all x, okay? So, so then, how do we find a and b at this point, okay? So there's a couple of ways. Actually, there's a couple of ways, but the book gives us a very easy way to do it, okay? And it says basically you pick, because this is, we're talking about equations and variables that could be any value of x, right? In this case, since we've multiplied it, we've kind of altered the, you have polynomial equal to another polynomial. Okay, so if we wanted to solve for, let's say, b, we could plug in x equals -2. So if we did that, we plugged in x equals -2, all we have to do is just plug it in and simplify and solve for b. Because why would we let x equals -2? What does that do? That cancels out the a, okay? It takes a away. So then you get -2 plus 7 is 5, and then the a cancels out because it was 0, and then you get -5b, and then when you simplify divide, you get b is equal to -1, okay? And then to solve for a, you would just let x equals 3, and then that would take out the b term, and you would get a is equal to 2, right? Because you would substitute 3 for x, you know, and do what we do and get a is equal to 2, 2 equals to a. So then finally, our partial fraction decomposition is x plus 7 over x squared minus x minus 6 is equal to 2 over x minus 3 plus -1 over x plus 2. So we can do this by using a graphic calculator to check it. All right. So this form of finding partial fractions are really, it's very nice when the denominator factors easily into linear factors, okay? But however, sometimes you're going to get a factor that's like a square term. It's quadratic, a prime quadratic, an irreducible quadratic technically, right? So we would use a different procedure, okay? So it's similar, but it's a little different, okay? So let's go ahead and it involves using system of equations. So this is why we're learning this now, because by now we should be super pros at systems of equations. Okay, so here we go. So let's write the partial fraction decomposition of all of this thing. X to the 4th plus 2x cubed plus 6x squared plus 20x plus 6 all over x cubed plus 2x squared plus x. So this is improper. What was the first step? Okay, is the numerator of higher degree than the denominator? And in this case, yes, 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 yes it is. So we go ahead and we divide it, and you can do that, you know, somewhere on the side in your notes or what have you. And then you would find that you get x with a remainder of 5x squared plus 20x plus 6. Okay, and then that's all over, you know, what you're dividing by, x cubed plus 2x squared plus x. So now we're going to split up the remainder part into fractions, right? Into partial fractions. We're going to decompose this. So you take the denominator and let's factor this guy, right? So we're going to factor it. You can pull out an x. You get x squared plus 2x plus 1. And then factor x squared plus 2x plus 1 into x plus 1 squared. Okay, so so because of that, we're going to include a partial fraction with a constant numerator for each power of x and x plus 1. Okay, so remember when I was talking about that repeated factors, that's what we're doing. So we have here, they're linear terms, right? None of these x's have a 2, right? So we can rewrite this remainder as a over x, that's one of the factors, b over x plus 1, because it's saying, okay, you have x plus 1, so that's one of the terms. You know, you need to write it from power 1 to, you know, m, however many, whatever multiplicity it is. So then you would do plus c over x plus 1 squared. So this is the general form of the decomposition. Okay, so the first step is really just, okay, let me find out what the denominators are. So I have an x, okay, I know x plus 1 is there, and then since it's squared, I need to include that. Okay, so now, how do I solve it? We always multiply by the LCD, which is just the denominator, and we cancel what cancels out. So on the left-hand side, you get 5x squared plus 20x plus 6 equals, and then you would get a times the quantity x plus 1 squared plus bx times x plus 1 plus cx, and that's the equation. We could do let x equals -1 and find c that way. So if we let x equals -1, you can go ahead and do this to practice, but you would get, you know, c is equal to 9, because you would have here, that cancels out the a terms, cancels out the b terms. Why? Because -1 plus 1 is 0 today, and -1 plus 1 is also 0. And so you would just get negative c, and on the other side you would get 9, okay? So if I do that, I get c is equal to 9. What if I let x equal 0? If I let x equal 0, well, that eliminates the b and c terms, and it gives me a. Okay, so I have here, you know, 5 times 0 squared plus 20, just plugging in 0. Okay, I get 6 on the left-hand side, and then the b term cancels out, the c term cancels out, and I'm just left with a, really. So a is equal to 6. So already by plugging in points, I have this, okay? And then finally, I've used everything, right, for x, the most convenient ones at least. So to find b, I'm going to use any other value along with whatever a and c is. So I'm going to plug a and c in now, and I'm going to choose one for x, okay? So I'm plugging in x, and since a is 6, boom, there's the 6 right there, right? And then 1 plus 1 squared, plus b, that's what I'm trying to find, times x, which is 1, you know, parenthesis 1 plus 1, and then plus 9, which is c, times our x, which was 1. And, you know, we just order of operations and stuff. So we just, left-hand side becomes 31, and on the right, we get 2b. Well, we get 24 plus 9 plus 2b, and then simplifying, right, and we get -2 is equal to 2b, and b is equal to -1. So that's everything we needed, yeah? So the partial fraction decomposition of the original, the big old thing, is equal to x, because remember we divided, plus, and then you have your a, 6 over x, plus b, -1 over x plus 1, and then plus c, which is 9 over x plus 1 squared. Okay, so that is a linear with repetition. Okay, so now let's do another one where you have a squared term. Okay, so let's see here, we want to write the partial fraction decomposition of 3x squared plus 4x plus 4 all over x cubed plus 4x. So this is a proper expression because the denominator is greater than the numerator. So let's go ahead and factor the denominator. And the denominator becomes x times the quantity x squared plus 4. So since this is, we have two factors. We have an x, a linear factor. So we're going to have to, when we write the decomposition, we know that it's going to be a denominator x and it's going to have an a constant, some number, we don't know yet, right? But now this is the new part. So when you have a squared term, we have x squared plus 4, okay? So that's going to be in the denominator. That stays the same. But now our numerator is different. Because it has to be of degree 1 less than the denominator, we get bx plus c. And that's the only new thing here, really. I mean, other than how we're going to solve it. Okay, but at least for this part, we're good. Okay, so the thing that's consistent, x is in the denominator. The other factor, x plus 4, is in the denominator. The only new thing here was this bx plus c. And that's because you have a square term. Okay, so now that we wrote that decomposition, we're going to multiply by the LCD, which is, of course, x times x squared plus 4. And then we get numerator on the left-hand side is equal to, and then a over x times the LCD will give us a times the quantity x plus 4, because the x's cancel out, plus, and then you get the x squared plus 4's cancel out, so bx plus c times x. Okay, now this is the interesting part. So let's really get into it. So I'm very excited. I actually like this part. So on the right-hand side, I'm going to distribute this a, and I'm going to distribute this x, okay? So what I'm going to get here is ax squared plus 4a plus bx squared plus cx. Now, let me just commute the terms and collect the like terms together, regroup it, right? So let's say here I have an ax squared and a bx squared. So if I, commute 4a and bx squared and I regroup, do a little regrouping, I get a plus b parentheses quantity a plus b times x squared, and then plus a cx, that would be the next one, and then 4a is a constant over here on the end. So notice I've written this in polynomial form, right? So a plus b times x squared plus cx plus 4a. Okay, so now this is the fun part. Okay, you're like, where's the fun part? I'm just kidding. It's all of it. It's all fun. Okay, so now that you have on the right-hand side a polynomial and on the left-hand side a polynomial, they're equal to each other. And the only way that two polynomials can be equal is if the coefficients of their like terms are equal. So let's camp out on that, right? So the thing that makes these two equal, right? The coefficient of x squared on the right-hand side has to equal the coefficient of x squared on the left, and so on, and also for x, and also for the constant term. Okay, so now I can write a system of equations actually. So let's see here. I have my coefficient of x squared was a plus b, so here it is. And the coefficient on the left-hand side of x squared is 3. So I have a plus b is equal to 3. Then for the linear term in the polynomial, you have cx on the right-hand side and 4x on the left-hand side. So c, the coefficient of x, is equal to the coefficient of x on the left-hand side, which is 4. And then comparing again just the constant terms, you get 4a is equal to 4. So see, we have 1, 2, 3 equations, but these are really easy, right? The system C is already given. Divide both sides by 4, you get A is equal to 1, no probs. Plug A back in, solve for B, boom. 1 plus B is equal to 3 gives you B is equal to 2, and that's it. So now I just plug it back into what I had before. So here's my A, 1 over x, plus my 2x plus C, which was 4. And that is it, people. Okay, so one more. You're like, yeah, I love this. More, please. I know. Okay, so here we have 8x cubed plus 13x all over x squared plus 2 quantity squared. Okay, so what does this mean? Now we have a partial fraction, but it's a quadratic, and it's repeated. It has multiplicity too. So what does that mean? So for our decomposition, that means that you have 8x cubed plus 13x over x squared plus 2 squared. is equal to, so we have to let, it's similar to the linear ones, right? We have x squared plus 2 by itself once, and then of course the numerator is now going to be ax plus b because we have a quadratic denominator, and then plus x squared plus 2 squared, quantity squared, okay, over cx plus d, okay? So that's the decomposition. Make sure you it makes sense to you, okay? And then, you know, the rest is very similar to what we just did. So we multiply everything by the LCD, okay? And then on the left-hand side, you will get 8x cubed plus 13x. And on the right-hand side, things cancel out. We get ax plus b times the quantity x squared plus 2 plus, and then this will totally cancel out, so we just get cx plus d. Okay, so then let's multiply this. The first two, you can do box method, FOIL, whatever. This is your result. You would get ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. So let's switch it around and write it in the proper format where the exponents are descending, right? They start from the highest and go down, you know, by 1. So polynomial form, in other words. So you have ax cubed, and then you have your bx squared term. Then you have a 2ax and a cx, right? They're both positive. So I put that in here. In parentheses, 2a plus c x plus, and then the last two constants, which is 2b plus d. Okay, and that's it. Gets its own little parenthesis. And then we get to do that fun thing where we compare the coefficients, right? So remember, so 8x cubed, so 8 is equal to a, right? B is equal to 0, yeah? Or 13 is equal to 2a plus c, and then 0 is equal to 2b plus d, and this is what it would look like. So you have a is equal to 8. They wrote it out this way, just, you don't have to write this incredibly large space after a. That's just to keep the form, you know. They want to keep it like this is column A, this is column B, this is column C, and column D. That's why. Okay, so A is equal to 8, done. B is equal to 0, done. Now we just have 2A plus C is equal to 13. Hold up, we already have A, it's 18, so I'm going to plug that in there, obviously, and I'm going to solve for C. And then we know that B is 0, so we're going to plug that in here, and of course we're going to get D from that. Okay, so yeah, so that's basically just, here it is written out, 8 plus c is equal to 13, subtract both sides by 16, you get c is equal to -3. And then plugging in 0 into the fourth equation, you would get 2 times 0 plus d is 0, so therefore d is equal to 0. So now I can go ahead and write my partial fraction decomposition. So the original rational expression is equal to 8x, so ax, right? Plus b was 0, and then plus, and then c was -3, so I just write up top -3x plus 0. So since d was 0, I just write nothing. Okay, so here we go. To solve, so just to recap, okay, what did we do? We have the guidelines, the linear factors. When we're solving the basic equation, we substitute the zeros of the linear factors into the equation. And when you have repeated linear factors, make sure we use the coefficients determined in the first steps to rewrite the basic equations. And then we substitute other convenient values for x and solve for what's remaining. Then the quadratic factors, we expand the basic equation, we collect terms according to powers of x, we equate the coefficients of like terms to involve equations using a, b, and c, and then we use a system of linear equations to solve for a, b, and c, and most of the times they're very simple, okay? So, and then of course, remember the first step was when you have a rational expression, if the numerator is of degree higher than the denominator, okay, we need to divide first and then do our partial fraction decomposition. Okay, so that is it for this section, and this is it, 7.4, 1 through 47 odd. And congratulations, we are done with, you know, learning new stuff. Okay, I will see you guys in class.